Hello, everybody. Welcome to the second installment for week 9. So we're still in section 3.2 of the lecture notes, and our theme for this second part is Cayley's theorem. So we're going to have a little bit more machinery in the next couple of weeks that are left to us, which will enable us to state and understand this theorem in a slightly more precise way than we'll do today. But really, in this lecture, what I'd like to do is try to explain what Cayley's theorem is about. I'd also try to explain something about the concept of isomorphism for groups, which we'll meet later in a slightly more full context, maybe. Okay, so to try to describe what Cayley's theorem is about, we're going to look at the group table for the dihedral group of order 6, which is a very nice group because it's the smallest example of a non-abelian group, and its group table is just about small enough to write out in full detail, but also big enough and detailed enough to be interesting. So what Cayley's theorem really says is that every finite group can be understood as a subgroup of the symmetric group of degree n, where n is the order of the group that we started with. Okay, so for example, Cayley's theorem says that every group of order 15 can be interpreted as a subgroup of the group S15 of all permutations of 15 elements, and same for any other n. Okay, so, and the way that that works can sort of be illustrated, I think, by just looking at the group table for some fairly small group, such as D6. So, okay, what are we saying about, what does Cayley's theorem say about D6? It says that it should be possible to interpret the elements of D6 as permutations of 6 things, and thereby consider D6 to be a subgroup of S6. S6 is the group of all permutations of 6 objects. Right, well, how could we do that? Well, if we look at the table here for D6, and if we just imagine that the kind of natural ordering or the sort of default ordering or home ordering of the 6 elements of D6 is to write the identity first, then the rotations through 120 and 240, and then the 3 reflections in the order TL, TM, TN. Okay, so there's no particularly good reason to choose this ordering. I guess it makes sense to put the identity first, maybe the rotations after that, but you know, this is a choice we make, which we call our kind of natural ordering of the 6 elements of D6. Okay, and when we look at the table, of course, what we see in each entry, if we look at the entry here, in the row labeled by the rotation through 120, and the column labeled by TL, what we're seeing is the symmetry that we get by performing rotation through 120 after TL. So it's the composition of rotation through 120 after TL. And if we look at what happens to all 6 elements after we compose them on the left with the rotation through 120, we get, of course, the same 6 elements again, but in a different order. Okay, so we get rotation through 120 after identity, that's this one, rotation through 120 after rotation through 120 here, and so on. So we get the 6 elements, but in a different order. So basically, the act of taking our 6 elements in their original ordering and composing each of them on the left with the rotation through 120 gives us a permutation of the 6 elements. It gives us the same 6 elements, but in a different order. And the same for every other element of the group. If we look at TL, look at the row labeled by TL. If we read the 6 entries in that row inside the table, what we get is the original 6 elements written in a different order. So we've got a permutation that's affected by taking the original ordering, composing everything on the left with TL, and coming out with a different ordering. Okay, so in this way, we can observe that every element, every one of the 6 elements of D6 corresponds to a permutation of all 6 elements that's just written into the row of the table. Okay, so through this idea of associating each element of D6 with the permutation that's written into the row of the Cayley table for it, we get an association of elements of D6 to permutations of 6 objects, and that allows us to interpret the 6 elements of D6 as permutations of 6 things. We still have to see why it's true that the composition of elements of D6 then corresponds to the composition of these permutations. That does turn out to be the case, and that's what Cayley's theorem tells us, that using exactly this kind of thinking for any group of order n, we can consider that group of order n to essentially be a copy of a subgroup of the group of all permutations of n objects. So this is a really nice theorem in at least one way, because what it tells us is that every finite group is a subgroup of a full group of permutations of a symmetric group. So this is one of the reasons why symmetric groups have a particularly important sort of role in the canon of finite group theory, because basically every single finite group is a subgroup of a symmetric group. So in some sense, if you want to understand all finite groups as thoroughly as possible, you have to understand all subgroups of symmetric groups. There's a downside though, and the downside is that D6 here it is. Okay, D6 is a group of order 6. We understand it well. We can write out this group table. It's a nice thing. This theorem of Cayley is telling us that D6 can be understood to be a subgroup of S6. The order of S6 is 6 factorial, which is 720. D6 is order 6. So D6 is really a really tiny subgroup of S6. So if we want to understand groups of order 6 by looking at a group of order 720, maybe that's not the most efficient thing. Okay, so Cayley's theorem is a theorem of very important theoretical significance because it tells us that all groups somehow live inside groups of permutations. In terms of its practical applicability, there's this problem that it puts relatively small groups inside absolutely giant groups. It puts a group of order n inside a group of order n factorial, which in practical terms is not necessarily ideal because you have to look inside extremely big groups to kind of see this theorem in action. But okay, so our plan now, in the next couple of slides, is to introduce the concept of isomorphism for groups. That's one important piece, which we'll be coming back to, but we'll see it here for the first time. And then to give a slightly more formal statement of Cayley's theorem and kind of an indication of a proof. But again, it's something that we might come back to a little bit later when we have a bit more language and terminology to go with it. Okay, so second item, the concept of isomorphism. This is something that is really important throughout all areas of algebra. It's important in other areas of mathematics as well, such as topology, for instance. Although the word isomorphism is not used uniformly, it is used in many instances, and there are other words that kind of play its role in other subjects, such as homeomorphism in topology. Okay, so an isomorphism is a relation that can exist between two groups. And what it basically describes is the situation where two groups are identical in all their structural or algebraic features and differ from each other only in the context that they're placed in or in the way that their elements are named. Okay, so here's an example. Maybe this example is a good place to start. So the example on the left here is the group of complex fourth roots of unity under multiplication of complex numbers. So the elements there are 1, the complex number 1, I, minus 1, and minus I. Those are the complex fourth roots of unity. And here is the table written out. On the right, the elements are the congruence classes of integers modulo 4, which are labeled by 0, 1, 2, 3. So the labeling 0 with the subscript 4 here means the congruence class is 0 modulo 4. So it's the set of all integers that are multiple to 4. The 1 sub 4 is all integers that are a multiple of 4 plus 1, and so on. And the group operation here is just addition modulo 4. So for example, 2 plus 3 here. 2 plus 3 is 5. 5 belongs to the congruence class of 1 modulo 4. So in this notation, 2 plus 3 is 1 mod 4. So the color scheme is supposed to suggest that the same colors appear in exactly the same positions in both tables. So if you were to compare the identity element here, the 1 of the complex roots of unity, with the 0 mod 4, which is the identity element for integers modulo 4 under mod 4 addition, then you'd see that the identity element shows up in exactly the same places in both versions of the table. It's the first item listed in each group, and it shows up in this upper left position and in these three sort of anti-diagonal positions in both tables. If we label the I of the complex numbers and the 1 of integers mod 4 under addition with the same color, we see again that that color appears in exactly the same position in both tables. Same for the green ones, which correspond to minus 1 in the complex roots of unity and 2 in the integers mod 4, and same with the purple ones, which correspond to minus I in the roots of unity and the congruence class of 3 modulo 4. So what we're kind of saying here is these two groups are different. They're not the same thing. They turn up in different places. They're interesting for different reasons. But as groups, abstractly, they look the same. So if you were to take the 4 elements, 1, I, minus 1, and minus I here, and just give them 4 different names, A, B, C, D. Do the same over here, give the names A, B, C, D to the elements in the same order, and just write out the group table with all the names substituted for A, B, C, D in that manner, they would look exactly the same. They would look identical. Okay, and that's what isomorphism means. It means that two groups are isomorphic if they're structurally identical, algebraically identical, and they would become literally identical if you replaced the names of the elements in each of them so that they matched. Okay, that's the concept of isomorphism. And generally speaking, although not always, group theorists kind of care about isomorphism. They consider two groups to be the same if they're isomorphic to each other. And they kind of care about showing that different groups are isomorphic to each other, something that is not at all obvious at first glance. So that's the sort of practical example that I hope might give a sense of what the concept of isomorphism means. These groups are both cyclic groups of order 4. The group of complex force roots of unity is generated, for example, by I or by minus I. Pardon me. Oops, that was accidental. The group of integers mod 4 under addition is generated as a cyclic group by the elements 1 or 3. And all groups that are cyclic of order 4 are isomorphic to each other. So another example is the group of rotational symmetries at the square, which is isomorphic to both of these, although again it turns up in a third context, which is not necessarily related to where we might encounter either of these two things out in the wild. Okay, so basically all groups that are cyclic of order 4 are isomorphic to each other. Okay, technically, an isomorphism between a pair of groups, so if we've got groups G and H with operations denoted by star G and star H respectively, just to be clear, an isomorphism between those groups is a bijective function from the elements of G to the elements of H. So basically a function that matches every group of G, every element of G to an element of H in such a way that all elements on both sides are matched. Every element in one group has a companion in the other, in such a way that not only are the elements listed off together, matched off together, paired off together, but that this pairing or this matching also respects the two group operations. And what that means is that if we take a pair of elements X and Y in G and look at their matches over in H, phi of X and phi of Y, if we compose them in G, the match of that element should be the element that we would have got over in H by taking the matches of the two X and Y and composing them in H. There's a typo here. This phi sub X should be phi brackets X. Apologies for that. Okay, so an isomorphism technically is a matching of the elements of one group to the elements of the other one that actually respects the group operations, in that it takes the composition of a pair of elements in G to the composition in H of their companions, their partners over in H. Okay, so here the matching would be the matching that according to the colors. Okay, to illustrate this particular isomorphism. So the color scheme here is supposed to kind of indicate what the matching is. Every element on one side is matched to its element colored in the same color on the other side. Okay, so two groups are isomorphic if they're basically algebraically the same, only differ in how their elements are named. Okay, with that in mind, we'll come to a slightly more formal statement of Cayley's theorem. So this theorem goes back to the middle of the 19th century due to Cayley, who was one of the founders of the subject that's now called group theory. Like many of the classical theorems of the subject, it now has a modern formulation that might not even really be recognizable to the person to whom it's attributed, which is in this case Cayley. The sort of formal definition of a group as we now know it came about a bit later than Cayley's time, or than the time of this theorem anyway. So it's so this is sort of a modern formulation of a theorem that can be traced back to Cayley and is attributed to him. Okay, so the theorem says if we have a group of order n, then it's isomorphic to a subgroup of the symmetric group of degree n, a group of permutations of n things. Okay, so that's the formal statement. What it's saying is every group of order n can be interpreted as a group of permutations of n objects. Okay, obviously not the full group of permutations of n objects, since n is a lot smaller than n factorial, but a subgroup, a group of permutations of n objects. Okay, so an outline of the proof, which hopefully makes sense in the context of the example on the first slide, where we looked at the example of the dihedral group of order 6. G acts on the set of its own elements by left multiplication. Okay, what does that mean? We know what a group action is. Take the set of elements of G. For any given element of G, we can permute the set of all elements of G by just hitting them all on the left with the one that we've chosen. Okay. That essentially means write out the row of the group table that's labeled by the element we have in mind, just as we saw for D6. Okay. Take all the group elements in your favorite order. Take a particular group element G, hit them all on the left with G, you've permuted them. Okay, so every group element in that way determines a permutation of the n group elements. And so for a given group element G, we'll write phi subscript G like this for the permutation of the elements of G that's defined in that way by left composition or left multiplication by G. Okay, so this is kind of complicated notation-wise, but go back to the example of the group table for G6 if you're confused by it. So, okay, so phi G for each G is a permutation of the set of elements of G. That means it's a function for the set of elements of G to itself. What it does to a given element X is just take it to Gx. Okay, we have a group operation in G, we can compose G with X. That's what phi G of X does to X. Okay, and we can observe that if we take two different elements of G, they determine different permutations. Okay, and if you think about the group table, that must be true. If phi H was equal to phi of G, if those two permutations were equal to each other, then they both have to have the same effect on the identity element here in place of X, which would have to mean that H would be equal to G. Okay, so this left multiplication action associates to every element of G a different permutation of the n elements of G, which is a key point because we want the number of, if we're going to say that G is isomorphic to a subgroup of Sn, then we want every element of G to be associated to a different permutation, and this job certainly does that. Okay, what we also want, of course, is that the association of our group elements to permutations should respect the arithmetic or the algebraic structure on both sides. In other words, taking a pair of elements of G, composing them in G, and then taking the permutation associated to that element should be the same thing as starting with our two elements in G, taking the permutations associated to both of them, and then composing them as permutations. Okay, and that's what this line is saying. That is true. If we take a pair of elements, G and H of G, and look at the permutation determined by their product GH. Okay, phi GH of X, by definition, X is an element of G. The permutation phi GH, what that does to X is multiply X on the left by the element GH. We're in a group, we have an associative property. So that's the same as multiplying X on the left by H first, which means taking phi sub H of X, and then multiplying that on the left by G, which means taking phi sub G of phi sub H of X. Okay, so we're saying that the permutation phi GH determined by the element GH is just the composition of the permutation determined by G after the permutation determined by H. Okay, so if you find this confusing, don't worry too much about it for now. Come back to it and sort of think about it some more, and maybe think about what it says about the case of D6, if you like. But basically, what we're saying is not only can we associate a permutation of n things to every element of G, but we can do it in a way that matches the group operation in G to the composition of the permutations that we're associating to those elements. Okay, we can also observe that the permutation phi determined by the identity element is just the identity permutation. It leaves everything alone. And we can observe, it follows from that in the previous comment, that if we take the inverse of some element G, the permutation that it determines is just the inverse of the permutation determined by G itself. So this set of permutations of n objects associated to the elements of G is itself a group. It's not the full group of n factorial permutations of n things, but it's a subgroup of it that has n objects. And so basically through this matching of an element of G to the permutation that's written into the row of the group table determined by that element, we can establish an isomorphism between G itself and a group of permutations of n objects, which is a subgroup of Sn, the symmetric group on n objects, or the symmetric group of degree n. Okay, so that's Cayley's theorem. And I guess the key thing to remember about this, if you're not going to remember everything in one go, is that Cayley's theorem tells us that every group of order n can be understood or can be interpreted as a subgroup of the symmetric group of degree n. Okay. This week's second weekly challenge what it tries to get at is the limitation of Cayley's theorem, which seems like it should be a really great theorem. It is a really great theorem, but in practical terms, like I was saying earlier, sort of seems like, oh, well, all we need to study then are symmetric groups, and then we understand everything about finite groups. The trouble is, symmetric groups get extremely large very quickly as n increases. So Cayley's theorem tells us that D8, the group of symmetries of the square, a very nice group that we know well, and that we can, write out the table for and everything. Cayley's theorem tells us that D8 is isomorphic to a subgroup of the symmetric group of degree 8, S8, the group of all permutations of 8 objects. Small problem. The order of S8 is 8 factorial, which is 40,320. D8 has order 8, so it's a really, really, really tiny subgroup of S8. So if we want to understand D8 by studying an S8, that's probably a bit of overkill. Okay. So Cayley's theorem recognizes that D8 can be understood as a subgroup of S8 by considering each element of D8 as a permutation of the 8 elements of D8, according to the group table of D8. Okay, great, that's very nice. But, could we realize or understand D8 as a permutation, as a group of permutations of fewer than 8 things? That's the question. And the hint is, remember D8, we understand it as a group of symmetries of the square. And every symmetry of the square can be understood as a permutation of the 4 vertices of the square, for example, or of the 4 edges of the square. So the question here is to ask ourselves, is S8 the smallest symmetric group that has D8 living inside it as a subgroup? Are there smaller ones? What's the least K for which the dihedral group of order 8, the symmetry group of the square, could be understood as a subgroup of the symmetric group on K objects? Okay, so a really good answer to this challenge would identify this K, this value of K, and also give an explanation to explain why no lesser value of K could be possible as the answer. But think of D8 acting on the vertices or edges of the square would be my advice. Okay, thank you everybody. That's it for the moment. We will see you later in the week. Take it easy.